area.
All right, lecture 24 today. By the way, it said lecture 22 last time. It was wrong. It was lecture 23. So today's 24. And a quick summary of what we're doing today is just a bunch of tests. You can see that there. Divergence test, integral test, comparison test, limit comparison test, absolute convergence, ratio test, and alternating series test. Lots of tests for these infinite series that we've been talking about. So let's first remind you what convergence of a series means. So we're given a series. If I just say the word series, it's implicit that it's an infinite series. Well, I'll go ahead and put the word infinite in here in parentheses. An infinite series, although I guess if they're in parentheses, I should put the word and. An infinite series, you could write it with summation notation. You should be comfortable with that. And you can write it without summation notation. You should be comfortable with that as well. Okay? The convergence or divergence of an infinite series is completely dependent on the convergence or divergence of the corresponding sequence of partial sums. The sequence of partial sums is a list of numbers you can create from the series. S1 is called the first partial sum. It equals the first term of the series, A1. Zoom in if you need to there. S2 is called the second partial sum. It equals the sum of the first two terms, A1 plus A2. S3 is the third partial sum. It equals the sum of the first three terms, A1 plus A2 plus A3, etc. Follow that pattern. In general, the nth partial sum is the sum of the first n terms. With summation notation, you'd write it like that. Without summation notation, you'd write it like this, where n is a positive integer, 1, 2, 3, 4, 5, 6, 7, etc. That's a sequence, not a series. A series is a quote-unquote infinite sum, though I hope you remember from last week, we're not literally adding up infinitely many things. Nobody can do such a thing. We are pretending that we are adding up infinitely many things, but it turns out that that pretending can be made rigorous, and it's also useful, amazingly enough. Okay? Like lots of things in calculus where we're kind of pretending something. You can make it rigorous. I'm about to make it rigorous, and it also turns out to be useful. Today we're going to focus on lots of tests. On Wednesday we'll focus on more tests as well as some proofs of these tests. We will do a couple proofs today as well, though they'll be in the context of using the tests. And on Friday we'll probably do more tests and also look at some applications. Okay? This is the sequence of partial sums. The series converges if the sequence of partial sums converges. And it diverges if the sequence of partial sums diverges. The series of the sum of the AKs converges, I'll just write CONV, if the sequence of partial sums Sn converges. And it diverges if the sequence of partial sums diverges. I'll put a /div in both spots. So the sequence of partial sums either converges or diverges. If that sequence converges, we say the series converges. If that sequence diverges, we say the series diverges. If the sequence of partial sums converges, like to 20 or 30 or whatever, the corresponding series is said to converge to the same thing. And we even write that it equals the same thing. If Sn converges to a number, call it L in general, then the series also converges to L. This is a K here. and we write that the series actually equals L as if we had added up infinitely many things, even though we did not literally do that. We are literally thinking about adding up finitely many things with these partial sums. There's no problem there, there's no pretending there. The pretending is with the infinite series. We're pretending we add up infinitely many things even though we are not. But we can still make it rigorous as far as what it means to pretend we are adding up infinitely many things. And the way you make it rigorous is with this sequence of partial sums. This is fundamental, and it's very confusing for people in general. These two things, the series and its sequence of terms, the A's, is very much related to the sequence of partial sums, but they're not the exact same thing. If your series is not geometric, at least, the very first thing you should try to do is you should check whether the terms go to 0 or not. There's something called the divergence test. Which is basically what you should always use first, at least if your series is not obviously geometric. You can state the divergence test in two ways. One way to say it is if your series converges, then the sequence of terms, the AKs, must converge to 0. That's one way to set the divergence test, but why am I calling it a divergence test if you don't see the word diverge in there anywhere? It's because there's an equivalent statement of this that does involve the word diverge. It's called the contrapositive of the original statement. Contrapositive of original statement. What is a contrapositive? Well, the word contrapositive is a fancy word from logic. It means take your if-then statement and switch around the roles of the things that come after the if and then, and also negate them. Like this. With this particular statement, if I switch around the things that come after the if and the then, if I switch their roles around, where do they come in the sentence? And I also negate them, meaning I start by writing saying, if AK does not converge to 0, so I'm making this thing come after the if now in this contrapositive, and also negating it by putting the word not there, then the original series, now it's going to come after the then, what would it mean to negate this statement? It would mean it does not converge, it diverges. It diverges. There we have a statement with the word diverge in there. These two if-then statements mean the exact same thing. This one's a little easier to prove directly. Maybe we'll do that on Wednesday. A little easier to prove this version directly. This is the version that's more useful, but they mean the same thing. And if this one's true, then this one must be true. I hope that makes sense, because if this series didn't diverge, if it converged, then this sequence would have to also converge to 0, which we're assuming it does not in this statement here. So I hope it's clear that these mean the same thing if you think carefully about it. It's the second form that we use. We can use it, for example, with a series like this. There's a series. Does it converge or not? It's not geometric. Look at the terms that you are adding, quote unquote. We're not literally adding up infinitely many things. We're pretending we are. They don't go to 0. They go to 1, in fact, as k goes to infinity. this diverges since the terms that are being added don't go to 0, they go to 1, which is not equal to 0 as k goes to infinity. I should really add by the divergence test. And again, if your series is not obviously geometric, that's always the first thing you should do. Is think about this divergence test. Do the terms go to 0? If they do go to 0, then maybe your series converges and maybe it doesn't. You need some other test. But if the terms, the things you're adding, don't go to 0, there's no chance for your series to converge. So the terms going to 0 is necessary for convergence, but not sufficient is the way it's phrased. In order to even have a chance to converge, the terms have to go to 0. Though if they do go to 0, that's not a guarantee. Which brings us to p-series. I want to do geometric series as well, but let's do p-series first. P-series, series of the form, add up 1 over k to the p power. If you're going to write that without a summation, it would be 1 plus 1 over 2 to the p, plus 1 over 3 to the p, plus 1 over 4 to the p, plus 1 over 5 to the p, etc. It's called a p-series. Now the p is an arbitrary letter to use. If we use q, we'd call it a q-series. But whoever thought of this first called it a p-series. This converges if p is bigger than 1 and diverges if p is less than or equal to 1. Fundamental fact you should know, okay? You can put it on your note card for the test, but you really should just know this like that. You see a p-series like that, you should know this fact that it converges if p is bigger than 1 and diverges if p is less than or equal to 1. Actually, if p is negative, like negative 2, you'd be doing 1 over k to the negative 2 power, which is the same as k to the positive 2 power. And the divergence test would guarantee it diverges when p is less than 0. Or p equals 0, in fact. So this is really only interesting when p is positive. But it converges if p is bigger than 1 and diverges if p is less than or equal to 1. How would you prove that? The best way is with the integral test, which is what you did for today's assignment. When you use the integral test, I'm not requiring proofs, either on the assignments or on the test. But I do want you to say what the function is. You want this quantity to be f of k for some function. And by the way, you know the book uses n often instead of k. And they say it's f of n. It's not a big deal. I prefer using k here. The book uses n, it doesn't matter. For some function f of x, where x is a continuous variable, considered for x greater than or equal to 1, although if we were starting at k equals 2, we could consider it for x greater than or equal to 2. If we were starting at k equals 3, we could consider it for x greater than or equal to 3. This function is continuous. It's also non-negative, greater than or equal to 0, for x greater than or equal to 1. I could say for x greater than or equal to 1 here as well. And it's decreasing. Also for x greater than or equal to 1. It's enough, in my mind, for you guys if you just graph it to verify that. The graph looks like that. Though you could verify it with a derivative that is decreasing. Its derivative, since it's the same as x to the negative p power, is negative p x to the negative p minus 1. And when p is positive, which is what we're really assuming here, this is going to be negative when x is positive. So the function is decreasing. Enough for you to just make the graph, though. Okay, we're fine with that. And what about the integral? What about the integral of f of x? We've done that before. Let's do it again real quickly. It's an improper integral. Should do it as a limit. A limit as b goes to infinity of the integral from 1 to b of x to the negative p. At least if p is not 1, this integral can be done like this. This is p is not equal to 1. If p does equal to 1, then the integral would be the integral of 1 over x, which involves natural log. We don't want to divide by 0 there either. You plug in b, and then think very carefully here about the power of b. You can figure out when this converges or diverges. The power of b is the key to focus on. If p is bigger than 1, what can you say about the power of b here? You could say it's negative. For example, if p is 1.1, then this power would be negative 0.1. If p is 2, this power would be negative 1. If p is 3, this power would be negative 2. If p is bigger than 1, negative p plus 1 is negative. Therefore, this would be better thought of as being in the denominator with the corresponding positive power. B to the negative p plus 1 is the same as 1 over b to the positive p minus 1 power. And if p is bigger than 1, that power is going to be bigger than 0. You're going to get something that goes to 0 as b goes to infinity. The point is, this converges when p is bigger than 1. If p is less than 1, then negative p plus 1 is bigger than 0. For example, if p is 1/2, this is 1/2. I really have the square root of b there, which goes to infinity as b goes to infinity. It doesn't converge. So this equals 1 over 1 minus p, or p minus 1 actually. 1 over p minus 1 if p is bigger than 1, and it does not exist if p is less than 1. In the case where p equals 1, we have to redo the integral completely because you get a log. But the natural log of b goes to infinity, diverges as well, does not exist. The upshot of all this is that this kind of integral converges when p is bigger than 1 and diverges when p is less than or equal to 1. Which, by the integral test, means, come back here with the camera too, this converges if p is bigger than 1 and diverges if p is less than or equal to 1. So if you believe the integral test, and you should believe the integral test, that's the quickest way to prove this. P-series give you convenient series to use a comparison test for. I'm going to do a bunch more tests today. It probably would be good to have your book open. I'm not going to write down these theorems because it would take too much time. But the comparison test is on page 512. It would be good to look at it there at the start of section 9.4. We could consider trying to use this comparison test for an example like this. I'm going to make it look kind of complicated. Does this converge or diverge? Pretty complicated looking series. Is the integral test something that could be used? Yeah, you certainly could try it. The corresponding f of x would be this function with an x in place of k. And that would be certainly continuous when x is greater than or equal to 1. And it actually also would definitely decrease to 0 as x goes to infinity. Would it be decreasing overall? I believe so, and I believe it's because you keep adding positive things here. That should decrease to 0. The graph should actually be fairly tame looking. And you could try to apply the integral test. The fly in the ointment would be trying to integrate something like this with an x instead of a k. Theoretically, it could be done with partial fractions, but I tell you, I wouldn't want to do it myself. And probably, because I sort of picked these coefficients randomly, probably it would involve irrational numbers when I try to factor it. And there'd be quadratics that I might have to complete the square for, and there'd be arctangents involved. It would not be pleasant at all. So trying to use the integral test, though theoretically possible, would definitely not be pleasant. Is there a better way? Yes, this comparison test is a better way. When you use this comparison test, on the couple problems I'm going to assign, I'm going to want you to write sentences. I'm going to want you to essentially do a proof, both with the comparison test and this another comparison test called the limit comparison test, which we'll talk about in lecture B. Proof, or I can write the word proof. Though if I'm going to prove something, I have to have a guess about what the answer is. Does it converge or diverge? Do you have a guess looking at this? Do you guess converges or diverges? Nobody? Okay, well, it's not surprising if you don't have a guess because it's complicated looking. But here's the key to guessing correctly. It's a rational function of k where the degree of the bottom is 2 more than the degree of the top. If it's a rational function that you're adding, and the degree of the bottom is 2 or more bigger than the degree of the top, it should converge because it's analogous to a p-series with p equal to 2 or 3 or 4. Why? This quantity acts like, not arc, but acts like k to the 4th when k is big. It's not really approximately equal to k to the 4th. It's more than it acts like it. What do I mean by that? Well, if you did graph this function that I circled here in red on some large scale, and I also graphed k to the 4th on that same large scale, on that large scale you wouldn't be able to tell the difference between the graphs when k is large enough, when you're far enough to the right. They'd be far apart in value because these terms would be large, but relatively speaking they are small compared to k to the 4th. For example, if k is 1,000,000, 10 to the 6th, then k to the 4th is 10 to the 24th power, whereas, for example, 5k cubed would be 5 times 10 to the 18th power. Both are big numbers, but relatively speaking, this is much bigger than that. In fact, it's 500,000 times bigger than that. Right? Thinking about those exponents, if you divide this by this, you get 500,000. So, even though they're both big, you can effectively ignore the lower powered terms when k is large. In other words, that means the whole ratio, k squared over k to the 4th plus 5k cubed plus 6k squared plus 4 acts like, and you might even be able to say is approximately equal to k squared over k to the 4th, which is 1 over k squared when k is large. And yeah, I mean, the ratio should actually be close there when k is large in value. Although it is more than just that they're close, it's that it's acting like this. That's a better description. Now we know the sum of 1 over k squared, being a p-series with p equal to 2, does converge. Therefore, we think this series converges as well. And that's what we will attempt to prove now. So how do you do your proof using the comparison test? We want to be kind of formal about this. We want to write sentences. And if you look at the comparison test, we need to identify an AN and a BN, or an AK and a BK, since I'm using K instead of N. You can use N if you prefer. Let AK be the general term of the series you're trying to prove the convergence of in this case. K squared over k to the 4th plus 5k cubed plus 6k squared plus 4. And let BK equal the terms of the series you know the convergence for, in this case 1 over k squared. In this case, and on your homework, I have made it relatively easy on myself to apply the comparison test. It's pretty clear, because I put the plus signs down here, that each value of AK is less than the corresponding value of BK. Because I'm adding positive things down there for the AK that are not there for the BK, making the fraction for the AK smaller than the fraction for the BK for any individual K. I can write that like this. I should also emphasize that these are non-negative quantities. 0 is less than or equal to AK, which I think I will write out here. Is less than or equal to, okay, get rid of everything on the bottom except the k to the 4th. That does make the fraction bigger because I made the denominator smaller by getting rid of these things. So I get a bigger fraction here, which equals 1 over k squared for all k bigger than or equal to 1. That's a condition in the comparison test. Look at the comparison test. In the comparison test, you're supposing that this kind of inequality, line of inequalities, is true to get to your conclusion. We should verify that in this case. And there's really no verifying to do. It's pretty obvious that this is true. Because I put plus signs there, and because k is greater than or equal to 1, so it's also positive, this fraction must be smaller than this one, because its bottom is bigger. I could have made it harder on myself by putting minus signs in there, and then this would not have been true, at least for small k. Maybe for large k it would have been true. I would have made it harder on myself. We'll do a harder example on Wednesday. But today we're making it easier on ourselves, and on your homework for Wednesday, it'll be easier. What do we need to show? We're trying to show the series for AK converges based on the fact that the sum of the BKs converges. So we should mention that the sum of the BKs converges. We know that the series, the sum of the BKs, converges because it's a p-series with p equal to 2, which is bigger than 1. So we're in the case where the p-series converges. Back over there. We know that. You don't have to reprove that. You can use it. Therefore, by the comparison test, the series we're interested in converges. Let's come back over here. Therefore, 3 dots means therefore, by the comparison test, or you could say the comparison test implies that the series we're interested in, and I won't bother rewriting the whole thing, I'll just put an AK there, converges as well. And you can put QED if you're done, or you can put praise the Lord. Okay? We're done. We're happy. There wasn't much of substance that we did there, but it is worth doing to carefully use the comparison test to identify AK and BK, to verify the conditions in the comparison test hold, that the series we're comparing to, in this case, converges, and therefore, by the comparison test, our original series converges as well. I said this with the integral test back before, and I'm going to say it again now with these series. I meant to say it. I said it with the comparison test for improper integrals back in chapter 7. And now I'm going to say it for these series. The summation signs here at the end must be there. It's the most common mistake people make in writing this stuff up, is they don't bother putting the summation signs. You will not get full credit if you do not put those summation signs there. Because that's what you want to know about. You don't want to know about whether the terms themselves converge. They do. Both of these things converge to 0. That's not the issue. I mean, it is important that they do converge to 0 so we have a chance of convergence. The issue is, does the series converge, the sum? So the sum must be there. It has to be there for full credit. I mean, I could even be real picky and take off, more than half the points if you don't put the summation there. I don't know that I would, but it's got to be there. Okay, that's the point. What about an example where you get divergence? What I'm going to do is I'm going to go through the whole spiel again and make appropriate adjustments. You may want to just watch and take notes later if you watch the video. I'm going to make a series that diverges here. And I'm going to pick k over k squared minus 1/2. Why did I pick a 1/2? It's a little strange there. I wanted to pick 1/2 because it's less than 1 so that I'm not dividing by 0 when k is 1. Now I could also avoid that by starting k at 2 or something and subtracting 1. But okay, we could do this kind of thing too. Does this converge or diverge? What does this thing act like? It acts like k squared when k is big. The 1/2 doesn't matter much. So the whole thing k over k squared minus 1/2 acts like k over k squared, which is 1 over k when k is large. Now we know the series whose terms are 1 over k, the harmonic series, diverges. Therefore, we think this series diverges. But to prove it, we want to use the comparison test. So I'm going to go back here and I'm going to do the proof. And I'm going to keep the structure here and make appropriate changes again, just like I did here. Let AK be the terms of the series you're trying to prove. Convergence or divergence for, in this case, it's going to be divergence. And let BK be the terms of the series that you know diverges in this case, 1 over k. The roles of the AK and BK in the inequalities will get switched around now. Actually, in the book, they call this AK no matter what and this BK no matter what. So perhaps it would have been better for me to switch around the lettering, call this BK and this AK. But I hope you're okay if I also just switch around the inequalities here. Now, I want to show this is bigger than or equal to that for all k. And it is. It's, again, pretty clear that it is. I could write 0 is less than or equal to 1 over k is equal to k over k squared is less than or equal to k over k squared minus 1/2. By subtracting 1/2 in the bottom there, I made the bottom of the fraction smaller, making the entire fraction bigger. So this inequality is true for all k greater than or equal to 1. We know This series now diverges. Therefore, by the comparison, this one diverges as well. The original series we want to know about diverges as well. Let's take our break. We will do a lot of other things after break, so we'll get a breath. Start again at 1:09.